Welcome everyone to this lecture where we will discuss Wagner and Kussner's unsteady aerodynamic model. Now recall last lectures we derived Theodorson's unsteady aerodynamic model, which solves for the unsteady lift coefficient of an oscillating wing. Remember that for this model to be valid, you had to have an oscillating wing with a constant reduced frequency. So for Theodorson, we solved for an aerodynamic model with a constant reduced, that is for a wing that is oscillating with a reduced frequency k equal to omega b over u, where omega is the frequency, b is half the chord length, and u is the free stream. So this model is invalid for a reduced frequency that is not constant, which means that if either your omega, your free stream, or your free stream are changing in time, your Theodorson in the format that we derived would not be applicable. And thus, it is useful to have theories in the time domain. So recall that for Theodorson, our input, or the input space we were working in, was the reduced frequency space, which means that you're solving for the unsteady lift coefficient for different reduced frequencies. Now remember that in Theodorson, lift was actually a function of the reduced frequency k, because the Theodorson function was a function of the reduced frequency. We would like to have theories where CL is a function of time or a function of reduced time instead, where S here is basically the distance traveled by the wing divided by half the chord length. So in this effort, we will look at two canonical problems. And the first problem, or the first model, is Wagner's unsteady model. In this model, we basically are trying to solve for the lift coefficient for a wing that has a step input of either free stream velocity or alpha. So, for instance, we are attempting to find lift for a wing where with the following motion profile, where u for the free stream velocity is equal to 0 for any t that is less than 0, or t equal to 0, and then y is equal to some constant, okay, for t larger than 0. Now you can say the same thing for the angle of attack. So instead of having an input of a step input of free stream velocity, you can have alpha equal to 0, again for t less than 0, or t equal to 0, and then alpha is equal to some constant as soon as t passes the 0 mark. And this input looks sort of something like this, where at any time, let's say this is t, and this is u or alpha, at any time prior to 0, you're at 0, and once you get to t equal to 0, you have some constant, either free stream or angle of attack. Now, the reason that those two sort of conditions, a step input and angle of attack and a step input and the free stream velocity are equivalent, is that a wing that is sort of at rest and just started, okay, a wing that is at rest at t less than 0 and then starts moving at t larger than 0 with a constant free stream velocity u, this case is equivalent to a wing that is moving at that free stream velocity at 0 angle of attack and then suddenly pitches to an angle of attack, a constant angle of attack at t larger than 0. So these two cases are equivalent, and thus the two-step inputs are equivalent. And I'm gonna try to formalize this in a better drawing. Okay, so I'm gonna have two cases, 1 and 2, where 1 t is less than 0 and 2 is t larger than 0. Okay, so a wing that is a wing at u equal to 0 for time less than 0, and then at t equal to 0 suddenly starts moving at some constant velocity, this is equivalent to a wing that is moving at that constant velocity, u equal to a constant, but at angle 0, and then suddenly once t passes the 0 mark, the wing immediately pitches at an angle of attack that is constant and equal to this angle of attack at that same free stream velocity. Those two cases are equivalent, and thus you can use Wagner to solve for either this condition or this condition. So moving on. This theory accounts for the delay in circulation growth for an accelerating airfoil. At angles of attack that are below steady state stall. Because remember, all these potential models rely on inviscid assumptions that really don't hold once you're in a stall condition. So remember, we rely on inviscid conditions and small angle assumptions that would not hold if you are at a high angle of attack and stalling. So this is sort of the sketch of the problem. You are solving for the CL of the wing due to some step input in either the free stream or angle of attack for a wing and its wake, or for a wing while representing its wake. So the airfoil starting vortex, which is this vortex here, induces a downwash on the wing. So basically, if you had this wing suddenly starting to translate without the development of a starting vortex and no wake, you would just have thin airfoil theory. But the fact is, you do have a starting vortex and a wake, and due to the nature of this rotation, it induces a bunch of downwash on the wing. And the effect of this downwash is to attenuate the coefficient of lift felt by the wing. So this reduces the local angle of attack felt by the wing and thus lowers the lift. No, sorry. Not lowers. Yep. It does lower the lift of the airfoil. But, I mean, intuitively this makes sense. If you have a sort of a free stream velocity in this direction causing some angle of attack, the downwash causes a downward component that sums with that free stream velocity, changing its direction. So rather than the free stream hitting your wing at this angle of attack, this change of direction causes it to hit the wing at an angle, reducing that angle of attack. So if we said that this is alpha 2 and this is alpha 1, alpha 2 is less than alpha 1. And since we know that the starting vortex is only in the vicinity of the wing for some short period of time and then it sort of convects away from the wing, this effect diminishes as the starting vortex moves away from the wing. And when it moves away from the wing, CL asymptotes to 2 pi alpha. So once this starting vortex moves away from the wing, the coefficient of lift approaches the steady state condition that is given by steady state thin airfoil theory. So how does Wagner's model accomplish its modeling task? And we're not going to go through the derivation of this like we did with Theodorson, but very similarly, he uses a line of continuous vortices shed from the trailing edge and terminating with the starting vortex. So again, if you have your wing right here, he uses a sheet of point vortices starting at the trailing edge and ending at the starting vortex. Now jumping into the solution of this model, the coefficient of lift for an impulsively started wing, or again, a wing with a step input in either angle of attack or free stream velocity, is the following. Where C is the chord, U is the free stream, and this is a delta function. And a delta function is simply equal to infinity at, or a really high value at t equal to 0 and equal to 0 otherwise. So this delta function at t equal to 0 jumps to a really high value, practically infinity, and is 0 otherwise. And this term right here represents the non-circulatory portion. And again, this makes sense. If you recall, non-circulatory portion or added mass relies on the acceleration of the wing. Now, if you look here, there is a jump in the free stream, which means that the derivative of this slope represents acceleration, and since this is a step input or a sudden jump in velocity, that goes to infinity. And then 2 pi alpha, alpha is angle of attack, and phi or phi of s is Wagner's function. And this bit right here, and I'm just going to move this to the side. This bit right here is the circulatory portion of the lift. Now, what is that phi function? Now that phi function is Wagner's function, and Wagner found that it evaluates to the function that I will plot right here. So for a plot where the x-axis is equal to s, and again, s is equal to ut over b, and this is the non-dimensional distance traveled by the wing, so it's the free stream times time divided by half the chord length, and this right here, y-axis, is phi of s. This function looks something like this. So 0. okay, it jumps to like pretty much infinity. Well, sorry, it actually does not jump into infinity. It starts at 0.5 and then slowly, as time increases, asymptotes to 1. This asymptote represents the approach to steady state. So as time goes on, the starting vortex moves to infinity, okay, and thus has no much influence on your wing. The conditions of the wing move to steady state thin airfoil theory, and thus this valuates to 1. This goes to 0, right, because you're no longer at t equal to 0, and c ends up being 2 pi alpha. So for t much larger than 0, okay, CL is equal to 2 pi, sorry, not 2 pi, is equal to pi c over 2u delta t plus 2 pi alpha phi of s. Okay, since t is a lot larger than 0, this goes to 0. And s approaches infinity, because t is a lot larger than 0, phi of s approaches 1. Thus, CL is equal to 2 pi alpha for t a lot larger than 0. Now, an important thing to note in this formulation is that for a wing with a sudden change in free stream, or sorry, not sudden change, but for a wing that is suddenly goes from 0 to a constant free stream flow, or a wing that suddenly goes to some angle of attack alpha, for those two cases, right? For the two cases above, the angle of attack change is the same over the entire airfoil. For instance, if you have a wing that suddenly starts moving or suddenly experiences some free stream velocity, each point in this wing, okay, simultaneously experience this change in the free stream. Likewise, for a wing that suddenly changes its angle of attack to some constant angle of attack, each point in the wing experiences this change of angle of attack. Now, this is important to note for the next canonical problem where we will not have this property. So moving on, we will move to Kussner's problem. And that is the problem of a sharp edged gust. Okay. So I'm gonna sketch here what this problem looks like. So you have 3 instants in time, okay? And then at t equal to 0, you have a wing that is entering a gust. So, well, in more accurate terms to this model, the gust moves towards the wing with a free stream velocity u. Okay, and then as t approaches, well, let's say this is t naught, at t1 larger than t naught, the wing has partially entered through the gust, the sharp-edged gust, and then sometime after t2 larger than t1 larger than t naught, the wing is fully immersed, like so, in the gust. Now, since we are solving this problem in the frame, in the body frame, or in the frame of reference of the wing itself is not moving. In contrast, the gust is moving to the wing with a free stream velocity. Now to sort of recap what I mentioned earlier, in this problem, a vertical gust with velocity w naught. So the velocity here in all these gust profiles is w naught. Approaches an airfoil as it convects with free stream u. And in this problem, the gust is semi-infinite, which means that the gust in this direction approaches infinity. And I'm sorry for this noise if it went through. This is the cat that we have. And another important point that touches upon what I said earlier about the Wagner problem. Here, the local effective AOA, or angle of attack, depends on whether or not the local chordwise station is in gust. For instance, if you take this case, okay, this portion here of the wing is experiencing the upwash from the gust, and thus it is experiencing some angle of attack at the local position. For instance, just gonna draw it in red here. A point inside the gust has a free stream velocity u and a upwash of wo, and this is some point on the wing. Thus, the resultant of those two vectors looks something like this, right at an angle, where this angle is I believe this, okay. This angle is alpha is equal to the arc tangent of WO over U. Okay, so the effective angle of attack at a point inside the gust is this value, which is obviously non-zero. So you have an angle of attack here, but you have zero angle of attack here. So the local effective angle of attack at chordwise positions on the wing depend on whether this position is inside the gust or not, where this is not the case in Wagner. In Wagner, once you have a step input, the entire wing experiences the same angle of attack all over it. So this is in contrast with Wagner. All right, and again, jumping to the solution. Here the solution is equal to 2 pi WO over U times some function psi, which is Kussner's function. That is a function of S, where S again is UT over the semi-chord length. And this bit here, WO over U, is the angle, is the sort of effective angle of attack using small angle assumption. Where, if you recall, I said that the angle here is equal to arc tangent of WO over U, right? So 2 pi of alpha is equal to 2 pi of arc tangent of WO over U, and using small angle assumptions, this is equal to just WO over U. Now again, the psi function looks something like this. Where you have 1 here and you have 0, and this is S, and this is psi of S, and it asymptotes to 1 for very large time scales. Once the wing is entirely immersed in the gust for a long enough period of time, again, we reach a steady state lift under these inviscid and small angle assumptions. And again, I do want to iterate that everything I just went through is presented in Leishman. Principles of helicopter aerodynamics, section 8.10 for Wagner, and section 8.11 for Kussner. So yeah, I'm just gonna, just for additional reference, you guys can consult these two sections in Leishman's book. And here I'm gonna give some useful approximations to these two functions. So for Wagner's function, phi or phi of S is equal to, one of the approximations is 1 minus 0.165 e to the power of minus 0.0455s minus 0.335 e to the power of minus 0.3s. And this approximation is attributed to R.T. Jones. And then another approximation is phi of s is equal to s plus 2 over s plus 4, which is a much cruder assumption attributed to Garrick, 1938. Now, obviously, this function is more accurate, but this function does have the upside that it is a lot simpler. So, in terms of like specific controls analysis, it could be preferable to use this function. But in general, I definitely would rather use this function when I'm trying to estimate lift forces using Wagner. And the approximation for Kussner functions are as follows. Psi of s is equal to 1 minus 0.5 e to the power of minus 0.13s minus 0.5 e of minus s. And this is in Sears and Sparks, 1941. Or alternatively, you can use psi of s is equal to s squared plus s over s squared plus 2.82s plus 0.8. So these right here, and I'm going to just box them. Are approximations you can use for Wagner's and Kussner's functions. I also did forget to mention something here that is really important, is that the t right here is 0, or t is equal to 0 when leading edge is just seeing the gust, which corresponds to this figure here. So this would aid you in evaluating this function. And then again, to help you evaluate this function, phi here of s is equal to ut over s, where again, this is not s, this is b. Where this buddy over here is evaluated at t equal to 0, which is the point where you suddenly have the step input in either angle of attack or the free stream. So this point here is when you start evaluating phi of s. So just keep those two things in mind when you are evaluating these Kussner's function and Wagner's function. And another little change I would like to make here is to move out, making this sort of slight adjustment to where saying that u is equal to constant starting at t equal to 0 rather than t just after 0. So again, this really doesn't change any of the dynamics here or how we solve the equations, but it would be a little bit more accurate to say that you turn on the step input at t equal to 0. So at t equal to 0. I mean, again, I think both statements can be correct. So you can either pretend that you are either turning the step input just after 0 or turning the step input at 0. I'm going to choose to turn it at 0. So at 0, we get this sort of step input, and this would make it a little bit more accurate to use the delta function evaluated at 0 to give you this sort of infinite response due to the added mass force. So yeah, just to recap the little change I made here, I decided to change my piecewise function to say that u, or the angle of attack, are both equal to 0 at any t less than 0, and then at t equal to 0 or larger than 0, u and alpha are equal to some constant in the respective cases, depending on whether you are evaluating a step input in the free stream velocity or a step input in the angle of attack. Now, a question here is, we have the steady state sort of, or not the steady state, the unsteady response of lift due to some step input. Okay, so given that we know response to step input, or another word for step here is indicial input, can we find the response to some arbitrary input? For instance, an S, well, yeah, and then we will, for example, just use an angle of attack input. Given that we know the step input change due to a step input angle of attack, we know from this input we can get the lift. Can we get the lift from any arbitrary input? Now, for linear systems, which we are working with here, again, remember, all the models we've worked with thus far are linear. For linear systems, if you know the response, the output response to some step input, then you can back out the unsteady response due to any input. Okay, so I will put that here if, okay, for a linear system, if you know the step response to, well, if you know the, let me expand this out. If you know the output due to a step response, you can back out output for any input. Sorry, not response. If you know the output due to a step input, you can back out the output for any input. And we can do so using a duomo or a convolution. integral. So this is a dual integral. Y of t is equal to f of 0 phi of t plus 0 t of df of dt phi t minus sigma d sigma. All right, so this here is the response in time, and f0 is the initial forcing or initial angle of attack. So for example, for Wagner's response, if alpha is equal to 5 initially before the maneuver, then f of naught is equal to 5. Now, phi of t is the indicial function, which is either Wagner or Kussner function in what we talked about earlier. And then you have this sort of integral term where df of dt is the derivative of the forcing. For instance, if you have an angle of attack response, not a step angle of attack input, but some arbitrary angle of attack input, then this is its derivative, okay? And that is multiplied by phi of t minus sigma, where sigma, well, phi is again the same indicial function, but now we have this input into this function, and sigma is a dummy variable that we integrate over from 0 to t, or in non-dimensional terms, y of s is equal to f of s naught phi of s plus s naught 2s of df over ds of phi of s minus sigma of d sigma. And all we did here was replace t with s, which is equal to ut over b, which is non-dimensional time. So how does this apply to, for example, our Wagner problem? So in Wagner problem, we can implement a convolution or a dual integral on the circulatory portion of the solution, because recall that the non-circulatory portion has some delta function, and that is essentially infinity at t equal to 0 and 0 everywhere else, so it doesn't really evaluate with the convolution integral. However, we can apply the circulatory portion to a dual integral, and the solution is as follows: of sigma s plus 0s d alpha of sigma over d sigma phi of s minus sigma d sigma, which is, again, it's just an application of the non-dimensional dual integral, where alpha of 0 is f of 0, and the alpha 0 sigma of d sigma is df d sigma. And we are evaluating this integral from 0 to the non-dimensional time s, at which we would like to evaluate the lift. So again, I'm going to try to go through this again. If you want to find the circulatory portion of the coefficient of lift at some non-dimensional time s, that is given by this term. And let's do an example to sort of solidify this. Okay. Let's assume that alpha of s is equal to 5 plus 5 of s squared. Now that means that alpha of 0 is equal to 5, And d alpha over ds, well, let's do this again. Alpha of sigma is just, here we're just replacing variables, and we're doing so to the derivative here, d alpha d sigma is just tan sigma. And then we can just evaluate this in the circulatory portion of the lift in Wagner. So CL at S equal to, let's say we want to find the lift at non-dimensional time, S equal to 2. Okay? That is equal to 2 pi alpha of 0, which is 5, times sigma of S equal to 2, plus we go from 0 to S, and again we are evaluating at S equal to 2, so we go from 0 to 2 of the alpha sigma of d sigma, which we found here, that is equal to 10 sigma, multiplied by the phi function going from S, which is 2, minus sigma d sigma. And you can then use one of the approximations. So here and here, use one of the approximations and solve the integral. And voila, you have the coefficient of lift at S equal to 2 due to this arbitrary change in the angle of attack. Now, for Kussner, again, a dual integral for Kussner essentially means that you have some, that means that you have some arbitrary gust that the wing is encountering. So if you have some arbitrary gust and you want to evaluate the coefficient of lift, you do a dual mill integral on Kussner. And the Kussner dual mill integral is given by the following. CL of S is equal to 2 pi over U of WO, which is the velocity of the gust at S equal to 0, psi of S plus 0 of S dWO of sigma d sigma psi of S minus sigma, where WO of S is the gust velocity experienced at the leading edge at time S. Okay, so the gust itself is a function of space. Okay, in inertial frames, if you're not really sitting on the wing, okay, if you're observing from the outside, you see a wing traveling into a gust, and the gust doesn't really vary with time, it just varies with space. However, if you are riding with the wing, if you are in the body frame of the wing, and you are sitting at the leading edge, you experience the gust as a function of time rather than a function of space. And thus, the velocity of the gust here is given by S, which is a non-dimensional time function or a non-dimensional time variable. Okay? So yeah, to reiterate again, this is some arbitrary gust where Okay, this gust, again in the body frame, the gust moves with a velocity free stream into the wing, and at every point in time, a different point in the gust meets the leading edge. And WO of S is the gust velocity that is experienced if you were to sit on the leading edge, okay, and for any time S. So for instance, WO of S is equal to 2 is the gust velocity experienced by you if you're sitting on the leading edge at S equal to 2.